Today we're going to look at section 6.3, which is separation of variables in homogeneous equations. The first thing I want to define is what it means for a function to be separable. So separable equations are equations of the type where we are able to separate all x variables on one side of the equation and all y variables on the other side. So we have this sense of being able to somehow sort of isolate each of them individually. Not necessarily solve for one, but isolate all of one type to each side. The first example we're going to take a look at is the square root of x squared minus 16 y prime equals 11x. So the first thing we need to do is get all the x's on one side, which is going to mean taking that x squared minus 16 square rooted to the right hand side. The other thing to remember too is that that y prime is actually dy dx. So if I rewrite this, I would have dy equals, I have my 11x, I have my division by the square root of x squared minus 16, and I have dx on the right as well. We're going to integrate this, and in order to do so we need u substitution. U is equal to x squared minus 16, and then du is going to be equal to 2x dx. So we don't exactly have a 2 in our equation, we'll divide that to the left, and we end up with the integral of y, which is y on the right, on the left, and then I have 11 halves integral of 1 over u square rooted du. Of course, this is u to the negative 1/2. So we increase the power and divide by the new power. We end up getting y equals 11 halves times 2u to the 1/2 plus c. Okay, I think I wrote that wrong. Let's try that again. 11 halves here. I think I said it right and wrote it wrong. And then obviously that these 2's are going to reduce, and I'm going to plug back in the variable I started with. This is 11 square root of x squared minus 16 plus c. And this is a general solution because we don't have any way to figure out what the c value is that makes this true in a specific case. Now our next example actually does have the ability to find out what c is. So we have our equation, our differential equation, 2x y prime minus the natural log of x squared equals 0, and then we know that y of 1 equals to 2. Alright, so the first thing that we need to do is to isolate those variables. So on the left hand side I'm going to keep my y's, and on the right hand side I'm going to move all my x's. So this is going to be 2x y prime equals natural log of x squared, and then I can rewrite this with dy. I can move the dx to the right hand side, and I have, because this is dy dx, right, so I can move the dx to the other side. I have natural log of x squared over 2x, and then dx on the right. Now in dealing with this 2 by properties of logs can come down to the front. So I actually can have dy equals, and that 2 that comes down the front will reduce with the 2 in the denominator, so this is actually the natural log of x over x dx, and I can integrate. Alright, so just like with the previous problem, this integration is actually an integration by parts. an integration with u substitution. The natural log of x is going to be my u, and then my du is actually 1 over x, which is a part of the problem as well, dx. So my integral on the left is actually y equals, my integral on the right is equivalent to the integral of u du. So y equals 1/2 u squared plus c. But we have this initial condition up here that tells us what y of 1 is supposed to be. So we have, again, y equals 1/2. But it's not just u. U is actually ln of x in this problem that is squared plus c. And my initial condition is that y of 1 equals to 2. So I'm going to substitute the 2 in for y and the 1 in for x. Natural log of x, though, is 0, so this is 0, and then 0 squared is 0 times 1/2 is 0, so we find out that c equals to 2. So my function is actually, or my equation is actually y equals 1/2 natural log of x squared plus 2. All right, we have one more problem in this sort of separable section, very similar to the last one. We have an initial condition that's talked about as a given point. It's the same situation. We have a function that's y prime, or an equation that's y prime equals y over 2x, and we need to find out if we are able to separate this. So first of all, this of course is dy dx equals y over 2x. So the 2x needs to stay put, the y needs to be divided to the left, and then the dx needs to be multiplied to the right. So this is going to be dy over y equals dx over 2x. Or if you want to write them, you could write them as 1 over y dy equals 1 over 2x dx. Keeping in mind that the 1 over 2x, don't lose track of what's happening here. Let me write it this way just to make it very clear. This is really 1/2 times 1 over x dx. So when I'm integrating this in just a moment, we need to keep that in mind. Alright, so on the left-hand side, we end up with the natural log of y. And on the right-hand side, we end up with the 1/2, and then the natural log of x. And each of these are absolute values. And then I have plus, and I'm going to call it plus c1 for the moment. Now, if you'll remember, what we need to do next from section 6.2 is we need to find out what this is in terms of y. That is, we need to solve for y. And the way that we deal with that, we'll come back here to the bottom for a moment, is we raise each of them, we make each of them an exponent of e. So I actually will end up getting a y equals on the left, and then the e to the 1/2. Well, I can't just cancel the e and the ln right away. I actually have to deal with the fact that this 1/2 is right here. It needs to be an exponent on the x. So if I have that as an exponent on the x, that actually will allow the e and the ln to cancel and give me x to the 1/2, which is the square root of x, which we'll get in a moment. The other component of this, though, is e to the c. So e to the c, right, if I had this written this way, okay, because I can do that because this is addition, I could separate this so that it ends up being e to the 1/2 ln x e to the c. E to the c is just some other constant, and we'll just call it c this time instead of the c1 that we previously had. So that's some other constant, and it needs to go, either you can write it before the x or after. I'll just write it before so that we sort of have it in the standard way we're used to seeing it. So this is actually y equals c square root of x. And we need to figure out what c is, and we can do that based on the initial condition that we're given over here. So when c is 9, y is 1, so we have 1 equals, not when c is 9, when x is 9, excuse me, y is 1. So when we put x in as 9, y in as 1, we find we have 1 equals 3c, and c is 1/3. So my function is y equals 1/3 square root of x.